Hello everyone, in this video we're going to be looking at another way to find in the volume of a solid of revolution. Okay, so to recap, last video we learned about what a solid of revolution is. Now a solid of revolution we learned was a region. The solid of revolution is a solid formed by revolving a region about a line. So this over here is an example of a solid of revolution. And we learned how to find the area of a solid of revolution, the volume of a solid of revolution, using an integral. Right? We learned that we can use small cylinders, small disks, and add up the tiny volumes of those tiny disks in order to get an exact volume. So this is our solid. Okay, so in this video, we're going to be looking at another case. Okay, so we have our axes again. And I'll just copy this. So I'll just copy this so I don't have to draw it again. So for this case, we're going to be looking at when a region such as this blue region, when that is revolved around an axis. Okay, so previously our regions were against the axis, okay, of revolution. For example, we might have taken this region. This region as maybe our region that will be rotated. But the blue region is the region that we'll learn how to do today, and is probably the hardest to visualize. Okay, so first we'll have to learn how to actually visualize these. So this region, which I'll color as blue, start here. Okay, so it will basically be this section rotating around so it's probably the hardest to draw. Okay, but you can see that this region, you'll have a hole in the middle, surrounded by the region. So you'll have a hole in the middle, and around that hole will be the actual solid. The actual solid. So you can start to see trying to draw this as symmetrically as I can. You can start to see what kind of looks like a solid, but with a massive hole in the middle. A solid, but with a massive hole in the middle. This is the solid we're going to learn how to take the area of today. It's not the neatest looking, but if you were to maybe get 3D software or something, you could maybe get a sense of what the solid will actually look like. Okay, so it will look like, okay, there will be a hole with the solid actually around it, kind of like a washer, which brings us to the method we're going to learn today, which is not so coincidentally called the washer method. The washer method. Okay, so we learned about the disk method. The washer method is similar in that we are adding tiny solids that we know the volume of, and we're adding all these tiny volumes. However, the washer method is different since you now have this region not touching your axis of revolution. So this is how your washer looks like. Okay, in case you don't know what a washer looks like, this is like a little donut hole. Okay, so this is your washer. And what's the volume of this washer? Okay, what is the volume of this washer? Now, to find the volume of the washer, okay, you might realize that it is the volume, okay, it is the volume of a big cylinder. So pretend it's like the center, right? If this was big R, okay, the distance from the center to the very outer edge, big R, it would be, and this is your height, H. You can see geometrically that it would be the big cylinder minus the volume of this hole, okay? And the hole takes the shape of a cylinder. So if we denote the distance from the center to the inner edge as little r, it would be pi little r squared h. Okay? Or we can factor out a pi and an h to write pi h times big R squared minus little r squared. Right? Because this tiny hole forms a cylinder, an invisible cylinder that is subtracted from the area of the much larger cylinder to get the area of this washer. Okay? So if we translate this to a graph, okay? Now, if you have an infinitely thin washer, then it will have an infinitely small height, okay? And that will be your dx. So that differential d is used when you're having an infinitely small quantity. So that'll be your dx, that'll be your height. Now, what is your big R, your big radius? So if this is your center, the center is the axis of rotation. So you're rotating it about the axis. Now, what is your big R? Well, your big R is the distance from the center to the outer edge. The outer edge is the top graph, right? It's the y coordinate, the y coordinate of the top graph. So this graph was F, and this graph was G, so y-axis or x-axis. And this is f of x. Okay, if we had to point x, this would be f of x. Now, what is this smaller r? Okay, the distance from the center, which we defined as on the x-axis, to the inner edge. The inner edge of our washer, if you look carefully, is the y-coordinate of the point on the smaller, of the point of the smaller function, the lower function, sorry. So that'll be g of x. Okay, so this red length is f of x, your top function, and this blue length, I shouldn't use blue, but this green length is g of x, your tiny function. So you can write the integral as volume equals, and you use this formula, except h is dx, and you represent big R and little r as functions of x. So it is equal to the int pi, since pi is a constant, you could take it out of the integral, from a to b. Okay, so this is your a, this is your b, and a and b are your points of intersection. Okay, you should recognize this by now, that the x coordinates a and b are the points of intersection. So you have a and b times f of x squared minus g of x squared. And now you have to realize how important it is to keep note of what the top function is and what the bottom function is. Okay, you have to be careful about what the top function is and what the bottom function is. Because if you switch them up, then you will end up with a negative answer. You'll have a negative value in the integral, and volume is a measured quantity, so it's always positive. So it's always positive, so you know for a fact that volume has to be positive. So it has to be the top function minus the bottom function times dx. Okay? And the integral means that we're adding up an infinite amount of infinitely thin washers. And the sum of the volumes of those washers will give you the volume of the entire surface. Okay, so if I were to draw a washer here, okay, and draw this middle hole, okay, you could see that this is a little less, but we account for that change in using the actual functions. Okay, and we get to add this washer and all the washers between this from A to B. Okay, and that is the washer method. So let's take a look at an actual example. Okay, so let's take a look at an actual example. So let's say that you had a function. Let's say I had a function let's not do that. So you had f of x equals x squared, times g of x equals 2x. Okay, so g of x equals 2x. And we want to find the volume when the region in between them is like 1. So you don't need to find out which. The region between them, as bounded by the graphs, is rotated about the x-axis. So let's draw our region. So I'm going to do my best to draw it. So you'll have a washer that goes like this, with an inner hole that goes like this. Okay, so that's our solid. So we want to find the volume of it. So where, first of all, they intersect at 0, 0, that's a given. And if you want to know where the x coordinate at which the two graphs intersect again, you could just set x squared equal to 2x. You get x squared minus 2x equals 0. And we see that x equals 2. Okay, because we already accounted for x equals 0. So we're basically taking the We're basically taking the volume of each washer between 0 and 2. So we have a formula, v equals pi times the integral from 0 to 2 of what's our top function? Our top function in this case is g of x equals 2x. Okay, so that will be 2x, okay, squared, 2x squared minus x squared times dx. Okay, and if you were to simplify this, pi times the integral from 0 to 2 of 4x squared minus x to the 4th dx. Okay, x to the 4th dx. Now what do? Well, you just integrate. Okay, you take pi and you integrate, so you get 4x cubed over 3 minus x to the 5th over 5. And you get, so if you do from 0 to 2, apply the fundamental theorem, you get, well, 0 will make the entire expression equal to 0. So we only need to evaluate it at 2. And that equals 4 times 2 cubed. So 4 times 8, 48 over 3. So that's just 16. Right? 2 times 8 is 16. So 2 cubed is 8. 4 times 8 is 20. 32 over 3, not 48 over 3. Woo. 32. Okay, this is dumb error on my part. So 32 over 3 minus 32 over 5. And if we were to actually subtract these fractions, okay, let's do that. So 32 times 5 is 160. So 160 over 15 minus 32 times 3, 96, minus 96 over 15. And that gets us, okay, let's just subtract real quick, 64. Okay, so we have 64 pi over 15. And that is the area, sorry, the volume, I keep on saying area so many times. That is the volume of, our solid. Okay, our solid of revolution by using the washer method. Okay, so we use the washer method. If we use the washer method, we get a volume of 64 pi over 15. Okay, now never mind, I already have that set of axes. So some AP questions will probably ask you to find an integral, the volume of a solid, revolved around another line. And this is where the washer method really does its job. So let's say you had sine of x. Okay, sine of x is a good easy function, almost at the time. And you're asked to, and you're revolving it around the line y equals -1. So what's the area of the solid made by revolving this top region? Okay, this top region around the line y equals -1. So this is where we get to use the washer method. Okay, because our region does not lie against the axis of revolution. So let's attempt to draw the solid. Okay, so if we were to draw our solid, okay, we'd have a little circle. That'll be the beginning of our hole, the end of our hole, and we would have this washer. Okay, I'm just going to draw a big washer down the center. Okay, let's draw a big washer down the center. Okay, so let's just leave the gaps open. So what is the area, sorry, the volume of this solid? Okay, so what is the volume of this solid? Now, we have y equals -1. Okay, so what is, so if we write our formula, we don't really have a defined f of x and g of x over here, okay? Since we're revolving about another line. However, we can define functions as f of x and g of x. So this is our x-axis. So our big R, okay, if we consider the center washer I drew, our big R, this is our center now on the line y equals -1. Our big R is equal to, well, this portion is sine of x. Okay, this portion is sine of x, and this portion is equal to just 1. Okay, because there's a distance from -1 to 0. So this portion is just 1. So the total big R, okay, big R equals sine of x plus 1. Okay, so volume equals pi times the integral from 0 to pi. Remember, sine of x becomes 0 again at x equals pi. Okay. From 0 to pi of our big R, sine of x plus 1 squared minus our little r. Okay, our little r in this case, to the inner edge, remember this is our washer, okay? So our inner edge is just 1 minus 1 squared. And we can evaluate this integral. 0 to pi of sine squared x, sine squared x plus 2 sine x plus 1 minus 1. Okay, so we'll just leave it like this. Okay, we'll just leave it like this. Now, using the trig identity we discussed last time, we can rewrite the integral we can rewrite the integral as 1 minus cosine 2x over 2. And let's have the 2 sine x also have a denominator of 2. So we can bring that denominator out. So 4 sine x over 2 dx. Now if we bring out that 2, we have volume equals pi over 2 times the integral from 0 to pi of 1 minus cosine 2x plus 4 sine of x dx. Okay, so we're going to start working our integral over here. Now this is not difficult to integrate, okay, because of that trig identity we pulled off there. So you have x minus, you can use a u substitution, get 1/2 sine of 2x minus 4 cosine of x from pi to 0. So what do we get? Now at x equals 0, x equals pi. we get pi minus sine of 2 pi is 0, okay, minus 4 cosine of pi. Cosine of pi is -1. Yeah, sounds about right. Cosine of pi is -1. So minus -4. So plus 4. Plus 4 minus, now we have to evaluate this at 0. 0 minus 1/2 sine of 0, 2 times 0. So that's, we're still at 0, minus 4 cosine of 0. Okay, minus 4 cosine of 0. And 4 cosine of 0 is 1. Okay, so that's minus 4. Minus -4. That equals pi over 2 times pi plus 8. Now what do we have here? That gets us pi squared plus 8 pi over 2. And that is our volume. Okay, that is the volume of this solid obtained by having this region that last time we evaluated to be when it was rotated around the x-axis, now when it's rotated about the line y equals -1. So the washer method works here as well. Okay, and it makes an all-around diverse way of finding volumes. It really expands the amount of shapes that you can find volumes of. Thanks for watching. If you have any questions, please comment below and like this video, subscribe, pass it on to your friends. Thanks for watching. See you next time.